Recall from basic algebra and arithmetic that there are certain properties that you can use to make your arithmetic or algebra easier to handle. Remember that these identities were the associative property, were basically for at least addition and multiplication, that if I have three quantities I'm multiplying together, that's the same thing as saying first multiply B and C and then multiply it by A, right? That's what we refer to as the associative property. By the way, the same is true of addition, although I'm going to do this specifically only for multiplication, just to shorten my work down here. Remember also that we have the idea of commutativity, where A times B is the same as B times A, although as we just mentioned, that's not true in matrix algebra, generally at least. We also had the distributive property, right? If we have two numbers we add together and then it's multiplied by another, that's the same thing as saying K times A plus K times B, okay? And we had a few more. Now, as it turns out, matrices and vectors have their own algebra and their own rules to work with. For example, if we have a matrix A and we take the transpose, of that matrix, we just get back the matrix itself. We already established, or maybe we didn't, that A plus B is the same thing as B plus A. Okay, that is, you can prove that by resting on the commutative property of basic addition. We also have a distributive property for scalar multiplication, which is the same as K times A plus K times B. That's true as well. We also have an associative property for multiplication, which is A times B times C. That's the same as taking the matrices, first multiplying the matrices B times C and then by A. Okay, that holds true. The same is true of addition, by the way. Okay, that holds true. And then we have some ones that are unique to matrices themselves and vectors themselves. So here, for example, if I have A plus B and I want to take the transpose of that, we get the transpose of A plus the transpose of B. That holds true. Interestingly enough, the transpose of A times B is equal to the transpose of B times the transpose of A. This should be an easy one to see. Take the transpose of an n by m times m by k, whatever, some other number, right? If we take the transpose of that, remember what we get. These are compatible matrices, so we get an n by k. And when you take the transpose of that, you get a k by n, right? But notice that the transpose of the B is k by m, right? And the transpose of the A is the m by n. We swap them. And that's why we have to put the B out in first place here and the A in second. It is not true. Don't confuse these. Okay, this is not true. In general, at least, it's not true. This is true because I just moved the transpose of the matrix. I'm doing the same thing just in terms of the transposes. And as it turns out, sometimes things are easier to work with that way. We do have the concept of an inverse matrix. I'm not really going to get into this at this moment, but the basic idea is that similar to how you have an inverse of a number in terms of addition, right? You have something like in the case of numbers, if I have the number 3, the inverse is -3, right? And we know that when we add that, we get what's called an identity, which is 0. But matrices work the same way, right? If I have A minus A, I get a 0 matrix, which is just a matrix full of zeros. Multiplication works the same way. In some cases, usually when it is square, and we'll get more into the dynamics of this later, but when I multiply, if an inverse for a matrix exists, then we get what's called the identity matrix, which, by the way, we've already discussed. That's the matrix of 1, 0, 0, 0, 1, 0, so on and so forth. It's the matrix with diagonals on it. Another property is if we multiply any matrix by the identity, we just get back that matrix. Square matrix. Got to be very careful with my terminology here. But anyway, you can see the operations in full effect. So, for example, suppose I had 3 times the identity matrix plus 5 times the matrix A, where the matrix A is, let's say, equal to 1, 0, 5, 1, then this is the same as, sometimes you'll see this, 1, 0, 0, 1 plus 5 times 1, 0, 5, 1. And working through the arithmetic of that, you'll see that we have 3, 0, 0, 3 plus 5, distribute the 5, 0, 25, and 5, which of course gives us 8, 0, 25, and 8, right? In terms of the other identities, if we can leverage those identities to simplify other more complex type of situations. So for example, suppose I have a matrix of numbers times an unknown, and this matrix, suppose, is a 3 by 3 matrix, and I have a vector of numbers, which is a 3 by 1, okay? What we'll find later is that if these are quantities of unknowns and these are quantities of knowns, if A has an inverse matrix, I can actually very easily solve my system of equations, which is what this is, by multiplying both sides by the inverse. You just have to be careful here when you multiply both sides and do algebra with the matrices that if you multiply both sides on the left, first of all, both sides need to be compatible. And second, you need to make sure you don't do just one on the left or one on the right. Okay? Due to the associative property, you can rewrite this as this. And we stated that anything multiplied by its inverse is just the identity matrix. And we stated that anything times the identity matrix is just itself. So as we can see, if we have a procedure to get us the inverse matrix, which by the way we will cover later, then we can very easily solve a system of linear equations by just doing basic matrix algebra. Okay, so you'll see this type of algebra appear all the time in advanced statistics, in machine learning, and econometrics. So you have to get used to just working with the matrices. But honestly, I know this looks like a lot, but it really isn't. It's just using, it's similar to regular algebra, where you're using the properties of the algebra and you're manipulating the symbols in a way so that everything follows the identities and you get a different type of quantity. Okay? The only thing you have to be more careful with here are the sizes of the matrices and how you're applying the operations. But put simply, those are the basic matrix operations.